All right, this chapter we are jumping into astronomical things. So we're going to be using the same words like forces, energy, these topics that we've introduced in previous chapters, and use them to describe planetary motion and things actually outside of our solar system as well. So the problem you see here, we'll be able to answer pretty quickly after we talk about Kepler's laws, and then we'll also introduce Newton's law of gravitation in this video, and we'll explore some of the consequences of this in later videos for this chapter. Okay, so your book quickly sums up where the world was when Kepler came along. So briefly summing that up, so Kepler was around before Newton. We'll get to Newton by the end of this video. Newton, the Newton's three laws and all that hadn't existed yet. Okay, so leading up to Kepler, so in the early to mid 1500s was Copernicus. I don't know how to spell Copernicus. I think that's got to be close. So Copernicus and his heliocentric theory. So the fact that the Earth goes around the sun. So he waited until he knew this would be a big deal and probably not well received. So he waited till he was close to death, I believe, to publish this. So this was around the mid 1500s. Copernicus and heliocentric theory. So the Earth going around the sun like that. And so before that, everyone knew for sure that Earth was the center of the universe. So this idea caught on in the next 100 years. So in the maybe mid to late 1500s, there was this really interesting person, if you read about him, named Tycho Brahe. I'm probably messing up that spelling too. Tycho Brahe, built there's so many stories about him that he built a house to measure very accurately the positions of stars and planets. So he would have a house and have this huge protractor, the size of his house to very accurately measure all this stuff. So he took a lot of data. So the main thing about him is he took lots of data. In addition to more interesting stories like getting into an argument about a mathematical formula and losing his nose, things like that. So he took a lot of data, hundreds and hundreds of pages of very careful observations. And Kepler, who was his student, so in the early 1600s, Kepler used this data continued taking a lot of data, and overall finally was able to sum up all of these observations in three laws of motion. So Kepler continued taking data, and formed three laws of planetary motion. Okay, so around the early to mid 1600s, the following was known from Kepler. So 1, the planets orbit the sun in elliptical orbits with the sun at one focus. Okay, so this is like an exaggerated oval. So an ellipse is a particular shape where, so for this one, the foci are pretty close to the edges. So this is an exaggerated version. What an ellipse is that it's it's the set of all points that have a fixed total distance to these two special points. So if you look at the sum of those two lines, the sum of the lengths of those two lines, it's the same thing as the sum of these two lines, or it's the sum of this plus this. Okay, so the set of all points having an equal sum of the distances to those 2 points. So the sun is here, and then your book says that Elvis is spotted here. There's nothing special there. There's nothing at the other focus. Okay, and this is exaggerated. The Earth actually, so even though the Earth orbits the sun in an ellipse, it's very close to being circular motion. The difference between between this point and this point is just a couple percent. And so that's why when you hear a number like the Earth, the distance from the Earth to the sun is 93 million miles or 150 million kilometers, that's true within a couple percent, 1 or 2%. It actually changes over the course of the motion. Right? Okay, so that's one of the laws. The second one is that planets sweep out equal areas in equal times. Okay, so again, using this oval with the sun right here. So if we wait like 1 day, and we're over here, maybe that's kind of exaggerated for 1 day, but so let's say this is 1 day. The area inside there would be equal to the area of 1 day here. So as the planet moves from here to here in 1 day, it looks like if it's closer to the sun, it's going to have to be moving faster in order to sweep out the same amount of area. Okay, so what we have in mind is that these areas, it's like this area in here and this area in here are the same. Okay. And in a later video, we'll talk about how this relates to conservation of angular momentum. Right, so this is a consequence. So it wasn't known to Kepler, but this is a consequence of the force being just straight towards the sun, why these are equal. But yeah, this was just looking at a ton of data and just noticing that this happened to be true. It's kind of amazing how it all worked out. And then the third one is that the square of the period, so let me write this down, t squared is proportional to the semi-major axis cubed. Okay, so because this is an oval, this distance right here doesn't have to be the same as this distance. So this distance is called the major axis length, 2a, and so half of that. So if you take the long side of the ellipse and divide it by 2, that's the semi-major axis length, a. This minor axis, we normally use the letter b for the length there. Okay, so you have to use the semi-major axis, and then this is the proportionality. So t is the period for one orbit. Period of one orbit around the sun. So it's the amount of time it takes for that planet to go around the sun. And this is the semi-major axis length. So if your planet's going approximately circular motion, that would be the radius of that circular motion. But in the case that you have an ellipse where A and B are very different, it's the A that's relevant there. Okay. Okay, so your book has it right there. So we're not going to prove this until the next video, but I'm going to jump ahead. And so Kepler didn't know. So Kepler could look at the amount of time it took to go around the sun. To measure the period and then the semi-major axis length and figure out what that constant is. So this is a proportionality. There's some constant there that's the same for any planet going around our sun. So for the sun, there's one constant there. He could figure out what that constant was from looking at data, but he couldn't prove what that constant was fundamentally in terms of other things. This is where Newton came in to save the day. So later on, we'll be able to prove in a following video So Newton came later. And showed. And I point this out now because you'll need this for a homework assignment. So t squared is actually, so that constant, so in order to turn that proportionality sign into an equal sign, that constant is 4 pi squared over g times m. So capital M is the mass of the sun. So it's whatever you're orbiting around. So the period depends on your semi-major axis length, and every different planet has a different value of A, therefore they have a different period. But that M is common to all of them. So this is the this is what you're orbiting around. So this is the mass of the sun in the case of our solar system. So you wouldn't plug in the mass of the Earth there. You'd plug in the mass of our sun to find out, for example, how far the Earth is from the sun in terms of the mass of the sun and then our orbital period, which would be 1 year. So if you plug in 1 year and you plug in the mass of the sun, you can figure out how far we are away from the sun. Okay, so we'll talk about that. We'll prove that next video, but I at least wanted to write down the result. Okay, by the way, your book writes down the mathematical form of the second law. Forgot to write this. Sweep out equal areas in equal times, so that rate at which the area is changing, so the area being, so these lines straight to the sun, dA dt is constant. So we'll also come back to that formula and prove that formula. Okay, so with those laws, we can already solve a couple problems. So before we move on to 7.2 and talk about Newton a little more, let's go back to this problem, the original problem here, and find out how long it takes for Mars to orbit the sun, right, using these two distances. So the fact that and again, so I just wrote down one distance there. I didn't mention that they're the semi-major axis lengths. But these, within a couple percent, these planets are very close to being circular around the sun. So with the exception of Pluto, which I guess isn't a planet anymore, this is not a bad approximation. Okay, so let's see this. Original problem. So we have I'm going to give these labels. So TE is the period of the Earth. So the amount of time it takes the Earth to go around the sun. So T squared is proportional to, and I'll call it the radius. So because we're specializing to a circular orbit, I can just replace semi-major axis length A with the radius of the orbit, R. T squared is proportional to R cubed. Now, I'm just going to replace this with an equal sign and just call it some constant. It's a constant that depends on the mass of the sun, but it turns out we don't need to know the mass of the sun to solve the problem that we have, right, to find the period of Mars's orbit. So we can write down the same thing for Mars. The period of Mars squared is that same constant, because the mass of the sun doesn't change, times the radius of its motion cubed. Okay, now we don't know what the constant is and we don't care about it. So I'm going to divide. So I have equation 2 and equation 1. So what I'm going to do is I'm going to take equation 2 divided by equation 1. Okay, so this gives me, so the left-hand sides say that Tm over Te squared is equal to C times Rm cubed over C times Re cubed. And see how the C's cancel out. Okay, so this is what I mean by the mass of the sun doesn't matter here in taking the ratio. So C's will cancel out, and we can write that this is the ratio of these distances cubed. And the point of the problem is to solve for the period of Mars's orbit. So I'm going to multiply by, well, first take the square root, and then multiply by Te. So I have Tm is Te times this ratio, Rm over Re to the 3/2. Okay, so by taking the square root, or raising both sides, so by both sides I mean the left-hand side and the right-hand side, take both sides, raise it to the 1/2 power, and then multiply by Te. We'll get you that equation. So we're almost there. The period of Mars's orbit is 1 year, which is the period of Earth's orbit around the sun. And now this ratio is 230 million miles. So the units are going to cancel out here. I could write out million miles, but then I'm just going to divide by million miles. Or sorry, not miles, but kilometers. So 230 million kilometers divided by 150 million kilometers for the Earth's distance to the sun. This to the 3 halves. And what you'll get in your calculator is 1.9 years. So remember, we assumed a circular motion, so we kind of used an average value. So this might not be exactly right, but if you look up the actual amount of time it takes Mars to go around the sun, this is pretty close. I think the actual result is like 1.88 or 1.89. Also, just the number of significant figures here. There's 2 sig figs here, so I'm keeping 2 here. So this is correct to within those two sig figs. It's almost 3 sig figs, but because these numbers happen to be close to 230 and 150. But yeah, we only wanted that much level of accuracy anyway. Okay, great. Okay, so that was so still pretty powerful, even in the early 1600s, with what Kepler discovered with those 3 laws of planetary motion. So this actually applies. So Newton, with Newton's laws, we can go back and prove a lot of these statements. And actually, this is true not just for orbits of our planets around our sun, but the orbit of any body around some central body. Okay. But we'd like to understand that. So we'd like to go back to understand what Newton contributed here. So later, so Newton was around in the late 1600s. Or Newton proposed his law of gravitation in the late 1600s. So early to mid 1600s was Kepler. 50, 75 years later, so late 1600s, is when Newton came along. Newton proposed his theory of gravity. So remember, he was the one who, so before the law of gravity, he had his laws of motion. Newton's first law, second law, third law. So the F equals sum of the forces is mass times acceleration, and then equal and opposite forces. So that came about just a little before this by Newton. And he used those laws of motion along with some previously known facts to get at the law of universal gravity. So what your book is doing in section 7.2 here. And what your book does is sort of shows some of the thinking that got Newton to his answer. Okay, so Newton already, just like we've already done problems here with acceleration as v squared over r, Newton already knew that, okay? So that formula, this fact doesn't directly help us here, because what Newton did with his laws of motion was talk about how acceleration was a consequence of forces. Forces are the more fundamental quantity. Acceleration is the result. So this formula relating kinematical variables, that's not going to help us. Well, we could maybe use that formula to help us clue in on what that force is going to look like, but the force isn't going to depend on velocity, for example. That's what I'm trying to say. So let's see what it could depend on. And this is what your book is getting at. So on Earth's surface, so what are we trying to do? So let's try and see the thinking here. See thinking that leads us to Fg equals, and as a spoiler of where we're going, the law of gravity is g m1 m2 over r squared, over some distance squared. Okay. So on Earth's surface, we know that the force, the gravitational force on like an apple on the Earth's surface, that's what your book is using, it's equal to the mass of that apple times some constant, times g. Okay. But g doesn't really vary points close to the Earth's surface. But we want to talk about a formula that's general enough that will work even for the moon going around the Earth. And the moon isn't close to the surface of the Earth. So what your book does is, instead of saying g, and it's talking about 9.8 meters per second squared, they're leaving it as a general function. So some function that depends on not just the mass of that apple, but the mass of, so it's what's pulling on the apple, it's the Earth. So presumably this will depend on the mass of the Earth as well. So I'm using lowercase m for whatever's pulling on the Earth, and the Earth is pulling on some mass, lowercase m, and then capital M is the mass of the Earth. And then this should also depend on the radius of the Earth, okay, how far you are away from it. So if this formula is also going to describe the moon going around the Earth, you could imagine this depends on the mass of the moon, the mass of the Earth, and then the only other thing that you could think that it could depend on is the distance between the Earth and the moon. Right? What else would there be for this function to depend on? So we also have some distance there. Okay. So the first step in trying to figure out what this function is what's so special about this mass? So the mass of the apple is maybe really small compared to the Earth, but when you're talking about objects as big as the moon, maybe there's nothing so special about this one as opposed to this mass. Okay, so, and in fact, if pretend the apple gets so big that it's much bigger than the Earth, now it's the mass of the apple that's the important thing. Okay, so because of the symmetry of that Newton's third law makes us think about how forces interact with each other, this requires a certain symmetry in how this whole thing depends on the two masses. Okay, so in thinking about objects that are really, really big and how there's no difference between that and the Earth, we can say that, well, this is going to be the two masses multiplied by each other. We shouldn't treat one any differently than the other one. Okay. Now, so because of that, I might label it M1 and M2, but I'm emphasizing that lowercase m is like the thing other than the Earth, and capital M is the Earth. So I'm kind of hinting that one is maybe a lot bigger than the other one, but not necessarily. And then this is going to depend on some function of lowercase r. Okay, so just the function of the distances at this point. Okay. Okay, so how do we get this other piece? So you've actually already done this in a homework problem. So remember, there was a homework problem that said that as long as this force goes like 1 over r squared is proportional to 1 over r squared, so this thing has to be 1 divided by r squared, then the moon has exactly the right acceleration. So if you take 9.8 meters per second squared and you multiply by the ratio of the radius of the Earth divided by the distance to the moon, so really the center of the Earth to the moon, to the center of the moon, radius of the Earth divided by this, and you square it. So this gives you exactly the acceleration required for the moon to undergo circular motion at its distance. So this is the bit I mean by we're going to combine our knowledge of this kinematics. So the fact that acceleration is v squared over r. So it was exactly that ratio that needed to be 1 over r squared to give us the right acceleration of the moon that led Newton to say, well, this should be proportional to 1 over r squared as well. So this is m divided by r squared. So your book goes over this logic as well, plugging in some numbers. So you might find that helpful to follow through the logic by actually looking at some of the numbers. Okay, so there's a proportionality here, and Newton just said, well, I can turn this into an equal sign as long as I put in a constant there. So we have some constant, capital G, m times m divided by r squared. So this is the magnitude of the force, and it's an attractive force. Attractive for both masses. So lowercase m pulls on capital M towards lowercase m, so they're both tugging inward on each other. So in other words, if I imagine lowercase m and capital M, maybe I'll do it like this. And there's a gravitational force remember, equal and opposite from Newton's third law, towards each other. This is what I mean by an attractive force. So Fg and Fg. And this radius, this r, so we didn't talk about like the spatial extent of this thing or anything. So this is exactly the same as the center to mass separation between these two things. So for a spherically symmetric mass, this is the center to center distance. So this r is center to center, not from the surface of one to the surface of the other. Okay. And you can actually prove that by taking this into a bunch of little chunks of mass and integrating over all the pieces. And it acts the same as if all that mass were just at the very center. Okay, so you can actually prove that. But it's, first starting out with this, you would just take the center, the distance from the center of the Earth to the center of the moon. That's the distance that you're going to plug into that formula. Right. This constant, capital G, is called the gravitational constant. And in SI units, this thing has a value of 6.67 times 10 to the minus 11. And for the units, so I know that that's the value in SI units. It's whatever units it has to have so that I'm left with newtons after all this stuff cancels. Okay, so this is newtons is going to be left over. And then I need to cancel all this stuff. Okay, so this is newtons, and then I need to multiply by meters squared, because when I plug in r in meters, that's going to cancel out, divided by kilograms squared. Okay, so if you remember the formula and you remember the number, you can just fill in the units later, because they're determined, just given that this is the number in SI units. Yeah, I think so. That takes us to the end of the section. So it's worth emphasizing that this gravitational constant, that doesn't depend on the mass of the sun. Okay, this is Newton's universal constant of gravitation. Okay, you would use this number even if you're talking about two stars totally outside of our solar system. What's the force from one on the other? Okay, so as long as you're not taking into account relativity, if things aren't moving close to the speed of light, then this formula is just fine to use. All right, so we'll explore more about this formula in a later section.